curious about a coil of coax? Well, I am too. I just bought this coax and it came in this coil. I want to take loss measurements while it's in the coil and then straighten it out and take another measurement and see how the coils affect the response of the coax. What do you think is going to happen? I'm not sure, but I think this makes a big difference, at least in this type of coil. So let's take our basic measurements, then we'll uncoil it and do it again. Okay, this may be an interesting little experiment. I showed you the coil of coax that I bought, and this is ABR-400. It's supposed to be equivalent to LMR-400. Okay, and I've got 150 feet of coax. Right now, we've got it on the 40-meter band, and I've got it set up into S21 log mag, which should show us our insertion loss. The SWR, I don't think is meaningful at this point at all. And then we have resistance, which is the magenta line down here at the bottom. So let's take the measurements here. For 40 meter, our log mag is negative 27.8. Our SWR is 9.8. We'll go ahead and get the next digit, 9.84 approximately. And our resistance at the top end of the band here is 10.51 ohms. I'll just say 10.5 ohms. So let's change bands now. Go to 14 and see if we get much change. Here we are at the 20 meter band, and at 20 meter a log mag is 28.5. This is in dB, that's insertion loss. The SWR is 7.24, we'll say, and resistance is 22.68. So let's go to 17 meters. And at 17, our log mag is 27.4, SWR is 6.6, and our resistance is 11.95. Go to 15 meters, and our log mag is negative 26.7. Our SWR is 5.9. And our resistance is 8.64. So let's go to 12 meter. Our log mag is negative 28.3. Our SWR is 5.8. And our resistance is 38.46. Let's go to 10 meter. And the log mag is pretty consistent across this, which is interesting. Negative 28, SWR is 5.9, and our resistance is 63.7. I hope this is all caused by this being in this coil. Otherwise, this is a bad piece of coax. I don't think it is a bad piece of coax. I think all these bad readings are caused by it's coiled up like this. Because I took resistance measurements with an ohm meter before I started, and it's, you know, there's no short, there's no problem with it whatsoever that I saw. So now I'm going to uncoil the coax, run it out of the shop completely, and then run it back in on both sides of the beast back here, coming in and out that door. And I'll close the door back on it just to keep everything the same, but this is very odd, and hopefully it's all caused by being coiled up like this. Thankfully, my hypothesis was correct, and what a difference it makes. Okay, on our log mag here at on 40 meters, we're reading that'll be 0.745 dB. 0.745, where before, when it was in the coil, it was 27.8. So very significant. The SWR is 1.073. So this begs the question, what if we just have a few coils? And we're going to test that after we get through taking these measurements. Then I'll pull some more of the coax in and make a small coil here on the desk and see if that has any impact on the readings compared to just straight out. Right now it's all stretched out, and, you know, as good as I can. I have to bring it back in close to put it on the meter. That's as close as it gets, is the leads on the meter. And the resistance here is 51.7 ohms, which is what we would expect, somewhere right at 50 ohms. Now we are taking, this is 150 feet of ABR-400, which is the equivalent of LMR-400, or close approximation to LMR-400. It's supposed to be a low loss coax. So let's go up to 20 meters. We've got a loss of 1.05 dB, and we have to divide these numbers by 1.5. All the specifications that the coax manufacturers provide us are either in per 100 feet or per 100 meters. To get to the 100 feet scale, we would have to divide these numbers by 1.5 since we've got 150 feet. And it would be linear. It's not logarithmic, it'd be linear, so just divide it by 1.5. Okay, and our SWR there is 1.04, and the resistance is 52.1. Let's go to 17 meters, and 17 meters is similar, negative 1.16, 1.06 SWR, and 50, may as well say 52 ohms. There you go. So let's go to 15 meters, 1.229, and I'll come back and divide all these by 1.5 so we can get a good comparison here if you want to compare it to the manufacturer specs or compare it to your own readings per 100 feet. Okay, our SWR there is 1.04, and the resistance is 51 ohms. Let's go to 12 meters, and that's 1.3. And you would expect the insertion loss to increase with frequency, as most all coax does. As the frequency goes up, your reactance, therefore your insertion loss, increases. So at 1.3 dB, and our SWR is 1.03. I have trouble with the zeros and the eights. 1.03, and the resistance is 51.8 ohms. Let's go to 10 meters. 1.441 insertion loss, 1.078 SWR, and 53.7 ohms. Okay, I'm going to divide all these log mag readings by 1.5 and come back and review those with you. Okay, the numbers look exceptionally good to me, and I think it matches or compares closely to the manufacturer specs. Okay, you can see here that for 40 meters, we've got a half a dB loss per 100 right here. For 20 meters, we got 0.7 dB. For 17 meters, we got 0.77 dB. For 15 meters, we got 0.82 dB. For 12 meters, we got 0.87 dB. And for 10 meters, we've got 0.96 dB. And that's the reason you buy low loss coax. For comparison, I've also got some RG-8X, and we're going to set up and measure that as well to see if it really makes a difference what type of coax you use. So after I get set up, we'll come back and measure the RG-8X and compare it to the ABR-400. Okay, I said I was going to test a small loop. So what I've got here is I've got 10 coils of the coax on the bench here. like you might do if your coax run is a little too long. You'd probably coil it up similar to this, either outside the house at the base of the antenna or wherever. But you probably are coiling your extra coax somewhere. So we're going to see if that has an impact on our readings. Okay, we've got our camera set up on the NanoVNA, got it reconnected, and taking our reading, first reading down here at the 40 meter band, and it has had some impact, but it's relatively small. We're reading 0.768 dB at 40 meters, and let's move it to the middle of the band there. Not a significant difference. Let's go ahead and change to 20 meters. Again, it has gone up negligible. It's about 1.09, negative 1.09, where before it was negative 1.05. I don't think it's going to make that much difference. Here we are at 17 meters, we're at negative 1.19, where before we were negative 1.16. So it doesn't seem to have a lot of effect for a small coil of coax. Negligible. You'd never notice it. You wouldn't notice it, and the people you're talking to wouldn't notice it. I mean, this is fractions, hundreds, literally hundreds of a dB difference. So no, it's not going to have an impact. Here we're at negative 1.24, where before we were negative 1.22. Go to 12 meters, negative 1.33, where before we were negative 1.3. And 10 meters, negative 1.467, where before we were negative 1.44. So it looks like we've got about 0.03 of a dB more loss or insertion loss when we have a small coil of coax. You know, if we've got extra coax at the end of our run. Where does it start making a bigger impact? I'm not going that deep into it, but you know, if you've got a small coil, you should be fine. You're not going to notice anything, and it shouldn't make a difference whether it's at the base of the antenna or near your radio. Just keep it to a minimum, I would say. Let's go ahead and go to the RG-8X now. Okay, I have 110 feet of RG-8X here, and we're going to do the same test to see what kind of results we get from it. We'll see if the insertion loss for this is greater or less than the LMR ABR-400. So let's measure. Okay, we've got 110 feet of RG-8X here, and we're going to do the same measurements. This RG-8X came from the Wireman, so that's the brand it is, and we'll see how it does. So we'll have to divide all the measurements I take by 1.1 since it's 110 feet. So the measurement on 40 meters here is negative 910, or that's 0.910 dB. So at 20 meters, we're reading negative 1.279, or just call it negative 1.28. It's kind of bouncing around a little bit. And the resistance is 51.58, we'll say. And I need to go back and get the resistance on 40 meters. And that's 49.05. We'll get the SWR also, 1.021. And the SWR on 20 is 1.071. So let's go to 17. Hadn't gotten in a rhythm here yet, so sorry about going back and forth. So at 17, we got a negative 1.41. We'll just say negative 1.41, 1.042 SWR, and 49.88 ohms. Go to 15 meters, got a negative 1.52 and a 1.033 SWR and 51.5 ohms. Now, we're going to test this too. This is in a coil. It may be better once it's strung out the door, and we'll check that too. So let's go to 12 meters. 12 meters, we're negative 1.57 dB, and we've got 1.066 SWR and 49.8 ohms. Well, that's varying. That's 49.05 ohms. And go to 10 meters. That's negative 1.69. SWR is 1.097, and the resistance is 48.2. Okay, well, let's get this strung out the door and measure it again and see how much it changes. It should change like the other one did. Okay, we've got it run out the door. It's fully extended. There's no coils in it now. Let's check 40 meters here. And at 40 meters, it's actually gone up a little bit. It's now 0.98, where before it's 0.91. So let's go see what it is at 20 meters. It's also gone up. It's negative 1.34, where before it was negative 1.28. So let's check 17, and it's negative 1.4. Have trouble with those zeros and eights. Negative 1.48. The previous reading, negative 1.4. At 15 meters, it's negative 1.6. It's gone up a few hundredths, 7 or 8 hundredths dB on each reading here. And I'm not reading the SWR and resistance. I don't think it's meaningful at this point. If I'm wrong, tell me in the comments below, but at this point I don't think they're meaningful numbers. So let's look here at 12, and it's negative 1.64, and at 10, negative 1.76. So it seems to have gone up about 7 hundredths of a dB by extending the coax out. And I think that has to do with the amount of inductance and capacitance. In my opinion, the RG-8X would have more capacitance. So the inductance was offsetting the capacitance, balancing it out, so to speak, and causing a lower insertion loss. That's my theory. I'm not an RF engineer, but I think that's because the RG-8X is thinner coax. So that means the braid is closer to the center conductor. So that should increase the capacitance. And the inductance, with it being in a coil, was offsetting that, so the capacitive reactance and the inductive reactance were balancing each other out more. It gave lower insertion loss. Both of these coaxes have a use. For longer runs, you need to look at the LMR-400 or the ABR-400 because they have less loss. Now, again, these readings that I just did on the RG-8X need to be divided by 1.1. But they're still much higher than the ABR readings, because the ABR reading at 10 meters was 0.96, and this is almost twice that. With RG-8X, you're losing over 1.5 dB, you know, above 15 meters. What is 1.5 dB? 6 dB is an S unit, so 1.5 dB is a fourth of an S unit. Are you going to notice it? It depends, but to get more power to the antenna, the ABR-400 or the LMR-400 is going to be a better coax than the RG-8X. Thanks for watching. Hope you learned something. Hope I learned something. This is a learning experience for all of us. This is Jerry, Kilo Mike 4, Zulu Kilo Bravo. Hope you have a blessed day.